Hi, everyone. Sorry I can't be there today. I wish I was, and it sounds like it's a great summer school program. And yeah, so I've been asked to talk about fire accident interactions at multiple scales. And so what I would like to talk about today are looking at turbulent processes and fire-induced winds at small scales, and then moving to large-scale wildfire observations, particularly looking at plume scale and what we can measure with both LiDAR and radar. And then I'll finish up with some complex terrain impacts on fire behavior with some examples, particularly looking at valley wind, horizontal winds and valleys, and also the canyon fire experiment, which some of you may know about. Okay, so basically the motivation is we know that fires are becoming more extreme, yet we don't fully understand the dynamics of how fire-atmosphere interactions play on fire behavior. Here's an example of the Car Fire tornado that was very devastating, equivalent to EF3 tornado. You can see a gas line wrapped around this tree, bark that was stripped off of the tree here on all the sides. If you look at all these trees, when we toured this area, it was complete devastation. And so we know that fires can generate their own weather, and it can be high impact weather and severe, and increases the behavior of fires dramatically. So I like to use Brian Potter's definition of fire interactions that are interactions between fuels presently burning and the atmosphere, and interactions between the atmosphere and the fuels that will eventually burn in a given area. So it's a fire-atmosphere interaction as long as the fire-induced perturbations are greater than the ambient variability in the state variables. This figure here from Adam Pachansky shows that you can have accelerated changes in the atmosphere due to the fire near the fire front, where you might get accelerated fire-induced winds, whereas the ambient wind away from the fire would be, standard logarithmic. And then obviously within the updraft, you get entrainment and mixing and development of pyrocumulonimbus, such. And we're going to try to talk about multiple scales, from the turbulent scale at the fire front and to the plume scale. This is a good example of how wind can impact fire behavior. Below is the 5 meter per second ambient winds with grass and grass fire versus the 1 meter per second ambient wind and rate of spread. Above, the bottom one with the higher wind speed, you can see that the smoke is more tilted, the column is tilted over more, and the fire's rate of spread is faster. Versus the 1 meter per second, where it's a slower rate of spread and the smoke gets deeper into the lower boundary layer. But if we look at an example with wind shear, where we have winds at the surface blowing from left to right and winds above the surface blowing from right to left, so wind shear is vertical wind shear, so basically winds in different directions in the vertical. You can actually have horizontal wind shear as well, but we generally refer to wind shear as in the vertical. So here's what happens when a fire ignites. It's blowing with the surface winds, but the plume is moving, bending over, and now you have fire spread along the flank that's becoming a head fire, and it's burning kind of backwards than it started. So just the fact that you have ambient wind shear, which is causing turbulence to form, shear generated turbulence, that impacts the fire behavior. And these are real world conditions. This is what happens in the atmosphere. Generally, in mountainous terrain, we get lots of different wind shears versus idealized flat terrain. And we'll talk about that later. But before we start diving into turbulence and these small scale structures, we need to define planetary boundary layer. So it's basically the influence of the air that's near the surface of the Earth that's influenced by the friction. And we call that the PBL, and there's other terms which we'll define in just a second. And we define the boundary layer as the part of the troposphere that is directly influenced by the Earth, particularly the surface stress, and its response to surface forcing, such as heat flux, at timescales of an hour or less. And so here's a classic cartoon example of what we should expect in the diurnal evolution of the boundary layer, where we start off in the afternoon with the convective boundary layer, CBL, showed by this mixing. As soon as the sun sets, we have cooling at the surface that then the surface responds by cooling. It then builds in depth of a stable boundary layer inversion that increases with depth. But the layer above the inversion is now called the residual layer because it's the layer that was formerly the CBL. So it's well mixed. It's just that there's no active mixing going on. And then we have a capping inversion in the free atmosphere. By morning, we have the buildup of the convective boundary layer. It starts very shallow, and it builds and builds and builds until it reaches its maximum. And the entrainment zone indicates where we have boundary layer air mixing with free tropospheric air and free tropospheric air moving into the boundary layer. So the convective boundary layer is important, and there was a very important paper published by Sun et al. In 2009 that showed that if you don't couple your simulations with the atmosphere, you can't get the spread right correctly. So these are burn probabilities for a number of fires in the convective boundary layer with coupling and without coupling. And without coupling, you just don't get the fire spread. And they basically showed in this paper that the convective boundary layer plays a big role in driving fires. So we can't neglect these basic processes that occur across the planet. So when we think about turbulence, you know, we've been talking about turbulence and wind shear and stuff, but we can define it typically or basically as a perturbation from the mean, where if we have a time series of data, a wind speed, u, and we take an average, which would be u bar, we subtract the average from the actual wind speed, and we get u prime, and that's that perturbation of u. And we can apply that to anything. So CO2 concentration, vertical velocity, temperature, etc. And so that leads us to defining turbulent flux, which is the covariance of any velocity component. Generally, we use vertical velocity, the covariance of a vertical velocity component and a quantity such as temperature, in this case theta, which would be potential temperature. And so we can then take a summation and take the average, which would be the over bar, so W prime theta prime bar, which would be our sensible heat flux, and we can then multiply that by density and such. So that gives us kind of a generic sensible heat flux, but we can look at this schematic over here where an eddy mixes some air up, some eddy mixes some air down, and that gives us a vertical velocity and a negative updraft and a downdraft, where you get the W prime is positive, theta prime is positive because it's warmer than the ambient, which is the red line here, whereas the parcel that mixes down, theta is now cooler than the ambient, and you have a downdraft. So those multiplied lead to upward heat flux, and so that's how we can define that using covariance. Now, how do we measure that in the field? Well, we use sonic anemometers, and these are deployed all around the world to measure ecosystem fluxes of CO2, methane, and water vapor and heat. And we can take those measurements directly from the sonic anemometer using covariance, and we know our density and heat capacity. We can then get our sensible heat flux. And there's a number of different ways of doing this. So what about thinking of taking these ideas and thinking about the fire front or the fire environment in microbiological terms in the near surface environment? Well, we can define a fire front passage just like we would a cold front passage. Fire front induced or fire induced winds. So this is a picture of the fire flux experiment from 2006. And there are multiple sonic anemometers on this tower. Grass fire was allowed to freely burn through it as a head fire. And then we can define the structure of the fire front passage to better characterize the micrometeorology of that fire front. We first proposed this, I think, back in 2007. We as meteorologists always talk about cold frontal passage or FROPA, but this is fire front passage. And so we define a pre-fire front, a fire front passage and then the post-fire front environment. And is characterized by increase in the state variables. So this would be U, V, W, and T in this example here. We can get a wind reversal. We can get a peak in turbulence sensible heat flux, obviously, because you have an increase in wind, you have an increase in temperature, then you would have an increase in sensible heat flux. And then also a minimum atmospheric pressure. These usually all occur at the same time in the same period, but not necessarily, they're not necessarily correlated. And then the strength of this determines that fire-atmosphere coupling. Here's an example of surface winds taken during the fire flux experiment. This is 1 second averages. So the wind speed and wind direction, we can see that in this period, right as the fire front approaches the tower, indicated by this maximum in temperature from thermocouples on the tower, we see a wind reversal of like almost 180 degrees. We're going from northerly to southerly. We have an increase from like 2 to 3 meters per second to 8 to 10 meters per second in wind speed. And then as the fire front passes, we get back to our ambient temperature and we get back to our ambient velocities and direction. The vertical velocity also shows an interesting feature. We have strong updrafts, but we have downdrafts behind the fire front. So I include this, it kind of indicates that we have air moving downward behind the fire front that helps maybe bring higher momentum to the surface, which can also increase the surface winds at the fire front. In terms of pressure, these are some data collected on a slope where we have vertical updraft, these little ideal, isolated updraft cores with the vertical velocity. They're very narrow. It's a very short period of updraft that passes the tower, and then the resulting drop in surface pressure of close to a half a millibar or half a hectopascal, and it's only for a couple of minutes that this occurs. So very transient, intermittent structures that we're trying to capture during the fire moving through instrumentation. So we went back to the Fireflux site in 2013. We did the Fireflux 2 experiment. It was a head fire, not perfect, but it was under a burn ban and red flag warning for the state of Texas, and it was very difficult to pull off, but we were able to do it. Here's a picture looking from a couple of different tower views. So here's the main tower looking, and there's a picture looking down off the top of the main tower at 60 feet or 20 meters. Here's a view from the observation tower of the ignition and as the fire is kind of burning through. What we have here is a composite of LIDAR winds, which are the shaded colors, surface pressure, which is the interior shaded area, surface temperature at the soil surface with the dots, and wind vectors from the anemometers that were placed within the plot and outside the plot. And so you see the kind of the change in the winds. It's northwesterly, but as the fire gets to the points, they get bigger and hotter. And so we have acceleration, but at the same time, we see a decrease in pressure by these shaded contours ahead of the fire front. And that's helping drive the winds and making them increase in velocity or in magnitude. But we can also look at the vertical because we had thermocouples on the tower. We had 3 anemometers ranged at 6, 10, and 20 meters above ground. And we can see that while there is some acceleration at the fire front indicated by the solid line of FFP, the warmest temperatures do not, they don't move upwards into the plume. They stay very close to the surface. So we're talking, ignition temperatures of 200 to 300 degrees C, staying very close to the surface. We do not see a strong wind reversal. We see the acceleration here with this big vector at 6 meters, but we do see a little bit of a wind shift ahead of the fire front. Most likely we've got flows moving around the fire front as indicated by these vector arrows up here. And then the pressure, it decreased ahead of the fire indicated here, and that's about 0.4 millibars, or about 0.3. So we see kind of the advection of hot gases near the surface just by these observations, and we can also see that winds at the fire front accelerate. We did another experiment on a slope with a crosswind. Here's some photos of the plume. It's fairly bent over, but we did get some indrafts that were crosswise to the mean streamwise winds, which were into the page. And then we have some, you can see the advection of or transport of smoke up the slope into the main fire front. And we were able to diagnose this using turbulent sensible heat flux in the vertical and horizontal. And so basically we just did the same thing for the vertical heat flux, but we sum the U and V, so U prime T prime bar, V prime T prime bar, and we were able to calculate it and show that at the surface we have some of the higher sensible heat fluxes in the horizontal. So that is, and this square is actually V. So this means that we have cross-stream, crosswise sensible heat fluxes moving perpendicular to the mean flow up the slope, while the main flow, there's still some heat flux along the downwind direction of the fire front, but just kind of shows that circulation that is forming at the surface. Whether or not this is plume overturning or actually a surface-induced fire-induced surface wind, it's hard to tell, but we can see that there is a strong magnitude of these fluxes. We can also look at the turbulent kinetic energy budget, which I'll show in more detail in another study that was just published this week. Some buoyancy, we can isolate buoyancy production and shear production, because those are the things that we can easily calculate, and measure, because of the instrumentation that we have. It's hard to measure the pressure correlation term without any pressure sensors set up spatially, and pressure that's actually measured at a high enough frequency. But what we see here is, in this case, that we had real strong buoyancy that surpassed the shear in terms of the production of the TKE. And these are the top panels show the variances of the velocities and the total TKE in the dashed black line, and then the different velocities components increasing as the fire hit the tower. And what you see past here is that we actually, at the surface, we don't actually have strong any measurements because the bottom sensor actually failed. So buoyancy reduction increased during the fire front passage due to a large increase in the sensible heat flux that I showed earlier. And in this case, the buoyancy production is larger in magnitude than the shear, which is surprising because it was a neutral boundary layer that day, cloudy, and quite windy. Moving on to even smaller scale, we can actually look at the spectra and the turbulence field using the sonic anemometer data. And again, we define that pre, during, and post fire front passage. We use a Morlet wavelet form transform to calculate the spectra. And following Mon and Obakov similarity theory, and I don't want to go into a lot of those details, but we can use normalized spectrum, and basically the energy, which is the vertical axis, and the frequency in the bottom axis. And what the similarity theory means is that given a certain stability class, we should have a similar curve where we have a peak in energy, due to larger eddies in this region, and then it tails off by a -5/3 slope into the smaller eddy sizes. And this is for no fire. This is just classic similarity theory over flat terrain. And we can use different scaling parameters like U star, friction velocity, or T star, convective scaling and such. But we had a number of different experiments, including the one I just mentioned, the grass fire and a slope. We had a subcanopy backing fire, a backfire, and a slash pile in Finland, and a grass head fire in California. And all these data were collected using the same sonic anemometers. And what we see in the no fire case is, so here's the normalized turbulence spectra. So we're normalizing it by U star squared, and we're normalizing the frequency by U, and we can get a classic. So this very thin line here is the classic KML curve that we expect. And so without the fire, we see that our largest energy associated with the turbulence is due to large-scale boundary layer eddies, and it tails off with less energy in the smaller scales. And that's for both U, V, W, and temperature. But when we add the fire, we actually see a flattening or an increase in the smaller energy, or smaller eddy scale. So eddy scale is decreasing as we go right. And we also see a very large increase in energy at the larger scales, but we see this flattening in W. So what that indicates, and in temperature, what that indicates is that we have increased energy, turbulent energy in the spectra due to smaller scale eddies being shed from the fire front. So now the turbulence associated with the plume is not just convective boundary layer turbulence, it's also very small scale eddies that are associated and generated by the fire. Just last week, a paper came out highlighting features of the turbulence from a number of different experiments, including fire flux from Desai et al. There's a great graphic that summarizes a lot of the structures that we can identify using the TKE budget, turbulent kinetic energy budget. And for the fire flux experiment, we've got streamwise, crosswise, cross-stream eddies. Streamwise eddies, we have turbulent kinetic energy outgoing fluxes and incoming fluxes, and due to transport, shear, and buoyancy terms of the actual equation. And so this panel here, this vertical profile of these terms, is the pre-fire, like ahead of the fire front, before the fire, before any influence of the fire, and the post-fire or fire front passage period, not post-fire, the fire front passage is indicated here. And what you see is that shear increases compared to the pre-fire environment. And also the transport term of TKE increases at least at the mid-level at 10 meters above ground. And so there's a strengthening of this cross-stream eddies. That's important in the context of what's been seen in some of the laboratory scale experiments, just seeing that cross-stream eddies affect hot gases to unburnt fuels, Finney et al. Furthermore, we can infer that downwash assist in fire spread because we have strong eddies that are moving with the wind. And so that's pushing the hot gases to the unburnt fuels as well. And this is something that we hypothesized in 2007, but this analysis diagnoses it much more clearly. And we also see near surface wind also seems to accelerate. So both analyses have suggested that. With these observations, we can actually diagnose a lot of the TKE and turbulent transport terms due to the fire and what may help spread the fire to unburnt fuels. And we need more data on these types of scales. So that's, some food for thought when we start thinking about measurement campaigns in the future. But again, I recommend this paper that just came out. Okay, so moving on to larger scales. The Rapid Deployments Wildfires Experiment, we sampled 40 fires in California with a number of different platforms, mostly a Doppler LiDAR, basically a Doppler LiDAR mounted on a truck. Here's what a LiDAR looks like. It can scan, full sky scanning. It measures velocity along the beam, and it measures aerosol backscatter. So we can identify plume structures, boundary layer structures, vertical velocities. We can also do special wind profiling, scanning routines that give us a vertical profile of horizontal winds and vertical velocities. And it's quite easy to just jump on drive out to a wildfire and make some scans. Here's an example from the El Portal fire in 2014, where we were able to get highly resolved plume structures with multiple scans. That's a photograph of the LiDAR at the fire. You can see it's not a very wide fire. It's approximately a few hundred meters in width, but it's fairly stationary, which is cool because that allows us to make multiple scans. And what you can see is this, highly resolved plume observations that we weren't able to get before. before we started deploying LiDARs on fires. And we also get very resolved structures, not only the backscatter of the plume, but also the velocity field. And so if we take the mean of that, we can get the plume center line based on plume cross sections of the backscatter, and assuming a Gaussian distribution. It lines up with Briggs very, very well in terms of this plume. So Briggs actually does work for some of these smaller or more idealized plumes. But we also can look at the mean velocity. This is radial velocity. So this is velocity along the LiDAR beam. So if the LiDAR beam is going from left to right, we have winds going away. In the red is away, positive velocities away from the LiDAR, and then winds blowing towards the LiDAR. We can see entrainment or convergent flow at the base of the column, and we can see real strong velocities up at the top of the plume, and then downdrafts at the backside of the plume as it's bent over. So that's compensating subsidence on the backside and overshooting plume tops. So plume's punching up and it's sinking back down. So we're able to get that in terms of averaging it out. What about inversion layers? So we know that inversions play a big role in fire behavior. We don't have a lot of quantitative analyses on this, but we do know that they are problematic for smoke management and for aircraft operations. Here's a capped boundary layer, a capping inversion that, the smoke gets trapped in it. Sometimes the smoke will then penetrate through. We have velocities, winds blowing one direction below the inversion and blowing opposite direction above the inversion. This is the Butts Fire in Northern California. Here's a better example of the Bully Fire, where you can see the inversion top here with the smoke being trapped, and then it penetrates and punches through. And then as it detrains on top of that inversion. And so the smoke doesn't enter back into the surface very well because it's being detrained along that, it's being decoupled along that temperature inversion. We can also measure larger fires and larger pyrocumulonimbus with airborne Doppler radar. I'm skipping a lot of radar basics in this course just because of time. But we had the opportunity through my NSF project to fly the Wyoming King Air, the Wyoming Cloud Radar over the Pioneer Fire in 2016, and it's actually the aircraft. You can't see it on the computer screen, but it's actually located here. We luckily found a photograph that showed the aircraft flying over it, and we believe that we've got some really unique observations. So for the first time, we were able to document vertical velocity structures in a pyrocumulonimbus. These are different legs. So flight legs are when you cross over the plume. This is, we also penetrated the plume multiple times, 3 times, but these are legs done with the aircraft above one section of the plume. Because the plume was, this is a mega fire, it was a very large fire, it was the largest fire in the US in 2016. We weren't able to get over the whole thing the whole time, but what we are able to do is take the average of all these velocities and get a vertical profile of the vertical velocity. We can see that the mean velocity, peak in vertical velocity occurs well above the surface, and that's also indicated by these white triangles. In this case, very strong, up to 58 meter per second updrafts that were very deep and had lots of structure occurred well above the ground. We also see very strong, close to 30 meter per second downdrafts on these edges as the plumes overturn on the edge. So these edge vortices can also be very, very strong. And this was published in GRL in 2020. You can access that paper. Another thing is what's inside these plumes. We have small cloud droplets, or are they non-zero pyrometeor concentrations. There's lots of ash and debris. Again, I'm skipping some of the radar basics that I usually put in this lecture just to kind of highlight what a dual polarized radar can do. And I'll give you some examples of one of our cases here. So we deployed to the Dixie Fire, which was a very large fire, close to 1 million acres. We deployed our Ka-band dual polarized Doppler radar, which is mounted on a back of a truck. We also deployed our LiDAR truck next to it, just off the screen there. And this is what happened as the fire ended up moving down the edge of the mountain. It came down, burned up over the crust within just a few hours, and generated 2 counter-rotating vortices. You can see one here spinning about 1 kilometer away from the radar. And we ended up probably staying for another 1 to 2 minutes after this was shot. And then we ended up driving, not because we were in an unsafe location, just because we were afraid that down trees across the major highway would probably trap us there for the day. And we wanted to get to another location. Here's what that looks like in the radar. So this is a horizontal scan, or a PPI, and you can see even the reflectivity rotating here on both these edges here, and we're talking about 2 kilometer width. Each vortice is probably about 500 meters in diameter, but maybe about 1 kilometer in diameter, and they're about 1 to 2 kilometers apart. And what happened was that the ambient wind is from the west. You can see it, this kind of arrow here, but the fire-induced wind began, and we could feel it at our backs as it was blowing up towards the fire, up towards the mountain. And generally, this is completely fire-induced. So we're talking multiple kilometers in length of a fire-induced wind that was observed. Our Doppler LiDAR was doing wind profiling. So in this period here, we can see that the winds went from westerly, which occurred most of the evening, to easterly, and all the way up to really, the top of the profile, almost 2 kilometers deep. So, there's lots of different shears and, things going on here, but we have real strong easterly winds aloft, which could be either a fire-induced wind or maybe the extension of the rotating column. So it's kind of hard to determine that with this data set here. But this shows the extent of what can happen to the what fires can do, what the plumes can do to the ambient winds. All right, so the last topic I want to highlight today are some examples from looking at kind of mountain meteorology aspects, and I've got a lot of collaborators that have contributed to this field, and I just want to acknowledge them here. But one thing that I always like to teach about in my fire weather class is just the idea that fire weather conditions can change rapidly. And so here's the onset of downslope wind storms, a Santa Ana wind event that impacted the surface. And so we basically drove down with the LiDAR and measured in the marine layer. So we were basically, my students were down there. They got down there at 5 a.m. and set up the truck and the LiDAR, and we're measuring the surface conditions. And you can see the winds are weak, 1 meter per second, variable, bouncing around everywhere. And then all of a sudden, just past 9 o'clock, the winds increased in velocity up to, gusting up to 12 meters per second and higher, averaging about 8 meters per second, totally out of the east. And so that happened right here at the same time. The humidity dropped and the temperature increased about 5 degrees Fahrenheit. So we're going from a cool marine layer environment that's, very benign to hot, dry, windy fire weather in a matter of just a few minutes. And so rapid changes in weather can cause rapid changes in fire behavior. And this can happen this quickly. And I don't think people a lot of times realize how fast the weather can change in even benign conditions. And the reason why this happened is if we look at LiDAR data, we can see that the winds at this time above the cool marine layer at the surface that we're observing at the ground were actually much stronger and blowing from the east. And it wasn't until they mixed down to the surface that we got those easterly winds that increased the temperature, because that descending air is warming, and it was drying, or it was drier air mass that affected the surface. And so that's what this looked like. We have marine layer air kind of blowing this way at very weak winds, about 1 to 2 meters per second, and then much stronger winds aloft blowing the opposite direction. So these are vertical slices of the LiDAR above that location. You can see that while it's weak at the surface, eventually, those winds mix down to the surface. And again, blues are towards the LiDAR, reds are away from the LiDAR. So this is a easterly wind blowing offshore. And we only have a range of 3 kilometers on each side, so we can't look at the entire structure of the flow. But this just shows how rapidly the winds can mix to the surface. Another issue is, so we're talking about vertical changes in wind speed, but what about horizontal changes? So horizontal variability of a long valley wind. So we deployed our LiDAR to Yosemite during the rim fire. I think that was I can't remember when that was, 2013. And we were able to do some horizontal scans across Yosemite Valley. And what you see here are the actual velocity. So reds are away, greens are near zero. So you see these are gusts. So these are wind gusts and turbulence, kind of just as the wind is blowing up the valley and bending around the bend there, or flowing around the bend. You can see there's lots of variability in just the horizontal winds throughout the course of the scanning period. And like if you see, we're going from like 8 meters per second to 0 within like 100 meters or 50 meters. A lot of weak winds, strong winds, just in that short distance. And so if we take an average of that, time average, so we can see that on average, the wind is accelerating around the corner here, but we have very weak flow and kind of convergence of just like weak winds at this edge here, which is, there's like a big bend in the valley here. So if a fire were to, basically start spreading in this valley, assuming the fuels are homogeneous, which they are not, we would expect that the fire might spread more quickly along this vertical sidewall of the valley and spread less quickly along this edge here. And we're not even considering, morning transition periods or evening transition periods, which could also modify the winds and the fire behavior. Okay, so I want to end on the California Canyon Fire experiment. I know some of you have seen this, but this was a collaboration with a lot of my colleagues who were there at the workshop, and funded by the National Science Foundation and through our center IUCRC program, which allows companies to participate in research projects, including and CAL FIRE. So this is a collaboration among all these institutions and CAL FIRE. So we had the opportunity to pick a canyon on private land that was part of a major prescribed fire program where burn block 1 and burn block 2 to the east were already burned out. So we had about 2,000 acres of buffer behind this burn block. And this is about 100 acres, the size of this canyon. You can see the scale. Winds are generally northerly to northwesterly because we're in the Salinas Valley, strong sea breeze coming in from Monterey. And this burn was set up to basically allow a head fire to burn up the steep canyon. And so there's a number of different instruments. I don't want to go through them all, but we had remote sensing, LiDAR scanning up the canyon. We had fire behavior packages. We had poles at the top with sonic anemometers. Here's what those look like. So they were actually, you can see them in the photo. These are 10-meter poles with sonic anemometers on them. The fire behavior packages were kind of located in this area here. And the ignition was down here. And our remote sensing facilities were down here kind of looking up at the canyon. So while it's, it doesn't look very, it's not too big of a canyon, but it's quite steep. Here are some of the instruments. We had the fire behavior packages. There's Alex Filkoff running with his. We had airborne with both a helicopter, that's the Swiss, which I'll talk about next, a drone as well. Alex's infrared camera was attached to the drone. We had our partners help us install our sonics on these poles, which were wrapped with a fireproofing material that was tested, our mobile tower, SODAR, LiDAR, radar, and a bunch of stuff, and weather stations. Here's a video from CAL FIRE from the top of the canyon, and you can clearly see that this was a high intensity fire burning quickly up a steep canyon. Flame heights were, probably 10 to 20 meters. We had flame lengths of 100 meters. We're still working on those calculations. There's lots of dynamics in this, and this is the largest canyon fire experiment ever conducted, and under pretty ideal conditions because we had weak ambient winds of 2 to 4 meters per second, and so the fire was able to just do its own thing. Here's the SWIS, the San Jose Wildfire Imaging System that was developed in-house using teleops and some other cameras and sensors, but it's really the software control system that it's really unique. And this is a picture of the system out of the helicopter for the canyon experiment. And this is Miguel Valero and the NOAA team, where we flew this instrument on a NOAA aircraft for the CALFIDE project. So these are some images of a wildfire as we flew over it. But this camera was hanging out of the helicopter here for this project. And I'm just kind of go forward a little bit. So this is sped up 10 times, but this is the canyon project, the canyon fire. And you can see, I believe this is the teleops. You can see classic V shape. So we've got, fire burning up one sidewall of the canyon, up the other sidewall. And now we're getting into the period of eruption where the fire is spreading more rapidly up the canyon center and up both the sidewalls simultaneously. And so you'll see the area growth pretty quickly here. So here's where it's really getting intense and erupting up the main canyon. Another thing I want to point out is you can see these bursts of cool air moving through the image. So that's those blues where it's cooler. And so we see advection of air coming in to the canyon itself. And so this is the first time fire eruption was captured with this high resolution imagery. We also are trying to get the georeference frames of those images. This is a work in progress that is we're working on, but we flew the whole plot with LiDAR and with multispectral cameras and LiDAR on drones. And so those data then, and we did pre and post. And so those data are allowing us to get a very high resolution DEM file for this analysis. Real quick, here's some data from the sonics. I just want to point out this bottom plot. So yeah, we got real strong updrafts, close to 20 meters per second as the plume was hitting those towers. Increase in winds and the shift in wind speed and direction. So about shifting from northwesterly to southerly and easterly as that wind kind of blew over the ridge top into the fire as the fire approached those towers, and that's indicated here. So real strong fire-induced winds that were measured at the top of the ridge line using these sonic anemometers. Unfortunately, two of the sonic anemometers were damaged in the fire. Here's the Doppler LiDAR that was scanning along the canyon. This is kind of the initial burn here. So backscatter intensity or aerosol on the left, velocities on the right, radial velocities. And so as the fire blew up and erupted, you can see strong fire-induced winds within the canyon bottom here. And that's indicated by the still image where we get real strong winds, above 10 meters per second. Ambient winds, again, were 2 meters per second. So real strong acceleration into the fire from outside the canyon. Okay, so I'm going to skip through these points just to save time, but I think the key points from the small scale stuff is that the fire front passage or FFP period is associated with increases in surface wind, turbulence, a wind reversal, and a pressure decrease. We see that on a number of different types of fires and different experiments. Those pressure perturbations form at or downwind of the fire front, causing the acceleration of the wind through the fire front. I talked about the velocity spectra at higher frequencies is due to the shedding of small scale eddies from the fire front itself, and we can see that increases the energy of the turbulence in the spectra. Let's see here, and then finally the plume scale. I showed you a lot of different fires and observations, including LiDAR and radar, but I just really want to kind of highlight that we need better observations. And so we've been funded by NSF to develop a fire plan. We're going to have 3 workshops next year, starting this fall with social science and community resilience. Next spring, we'll do an observational field campaign planning, and followed by a modeling session that will be led by Albert and Arnaud. So stay tuned for that. And if you have any questions, please feel free to reach out to me. And thank you very much. And I'm sorry I'm not there. I really bummed about that, but hope you have a great time with the rest of the workshop. Thanks.